Today we're starting the second major topic of this course, which is the integral part. And there are going to be various different integrals. And the first ones we're going to encounter are called double integrals. But before we talk about them, I want to give you a brief, very brief reminder of integrals from Calculus 1. So the motivating idea behind integrals in Calculus 1 was the following. Suppose you have a function, single variable function. Let's say the graph looks something like this. Maybe I'll make a, no, we don't need a bigger drawing. Okay, here's the graph of some single variable function, f of x. And for simplicity, for the sake of just a reminder, let's assume that it's continuous and it's positive, and here is A and here is B, and we're interested in the area under the graph above the x-axis of this function f. So we're interested to know what is this area here. This. And the way we did it, so in general, before learning integrals in Calc 1, the areas we know are simple geometric areas. We know how to find the area of a triangle, the area of a circle, the area of a square, and this is not one of those, obviously. And what we do is we subdivide the interval. Remember what the formal word for this subdivision was? Starts with P. Partition. Did you use that word? Okay, so terminology that maybe you haven't encountered. This is called a partition of the interval AB into subintervals, which are not necessarily of equal length, as you can see. On each one, in each one, we choose a point, whatever point we want. So here's a point in this first subinterval, and here's one in the second subinterval. We evaluate the value of the function at that chosen point. And then we construct what we call a Riemann sum. So we take these rectangles, which are based on the partition. So when we just consider the partition, what we get is not exactly rectangles. Three sides are straight lines, but the top is still the graph of f, right? So what we do is we take the top, instead of the actual graph of f, we take the value of f at that chosen point and declare that the top of the rectangle. So we get a rectangle here, and here's another one here, and maybe here we chose this point, so we get this, and here maybe we chose the bottom point and we get this. Let's make slightly less so we don't have to work so hard. So in this final segment, let's say this fat rectangle is one segment in the partition. We get again a value up here, and we get this. And what we do know is to calculate the area under each orange line, the area of the rectangle, which is just the length of its base times its height, right? So if we, let's start using some names here. So let's call these xi. So this is x1, x2, x3, etc. A is x0, and B is xn. These are just the points we chose in the partition. And then these blue chosen points here, at which we evaluate f, let's call them C1, C2, and so on. Bless you. And then the area under the orange lines, the sum of the areas of the rectangles, is given by what we call a Riemann sum. So it's the sum, I equals 1 to n, of the areas of the rectangles, which is the length of the base of each rectangle, which we usually denote by delta xi, times the height. The height is the value of the function at this chosen point, f at ci. So do you agree that this sum is the sum of the areas under the orange heights that we chose? Okay. Now this is not precisely the area under the graph, obviously, because we have some differences here, which can be significant. And the way we get closer, the way our approximations get better, is by a process where we make the partition more delicate. We choose more and more points instead of choosing 1, 2, 3, 4, 5 segments here. We can choose 500 segments or 500 million segments. Okay? And there's a formal definition behind this. It's rather subtle, and I'm going to just, in order to just give the idea, which is what we're going to do in the multiple integral case, I'm going to be a bit unprecise and just say that in the limit, so this is maybe in not too formal, in the limit, when we make the partition more and more and more delicate, the formal terminology is refine. We're refining the partition. Okay? So under this refinement process, eventually we get arbitrarily close to the actual area under the graph. And this area under the graph is denoted by the integral. The integral is denoted by a snake. This snake originates from an ancient version, well, not that ancient, but an older version of the letter S. It comes from the word sum, or summa in Latin, the sum, the integral of f of x dx, which is the area under the graph. Okay? So does everybody kind of recall this and get the idea and understand the process here? Okay? What we want to do now is generalize this at first to a double variable function situation. Okay, so what's going to be the picture? Again, first without being too formal, and then we'll formalize it gradually a bit more. So the situation now is that we have a function in 2 variables. And for starters, let's assume that it's defined on some rectangle. Okay, so here's the domain. Remember, the domain lies down here in the xy plane. And the domain is some blue puddle over which it's defined. And let's assume that the domain here, in this case, let's call it D, is in fact a rectangle. Do you see that this is a rectangle? Okay, it just, in perspective, so let's say that this is the value on the x-axis, we're between A and B, and on the y-axis, we're between C and D. So the domain here, the domain is AB cross CD. So are you familiar, do you know what this x here means? Okay, so this is a product of 2 sets. And what we mean by a product of 2 sets is all the elements which are ordered pairs, an element from here and an element from here. Okay, it's called a Cartesian product. And what I mean here is all the points x, y, such that x belongs to this set, the interval AB, and y belongs to this set, the interval CD. Okay? So do you understand what I mean by this notation? It has nothing to do with a vector product. These are not vectors. And clear? There are not many available notations for products, and there are much more different products than signs to denote them. So it's either a dot or a little x or nothing, and this is a little x situation. Good? So this is precisely this. X is between A and B, y is between C and D. Good? Okay. Now we have a graph of a function which lies where? Show me with your hands. Exactly. The graph of the function is somewhere up here in this situation, right? So let's draw it. Maybe let's take a different color. Let's say red. So the graph of the function is somewhere up here. And I don't know exactly what it looks like. Let's say it looks something like this. Okay, so this is fxy, the graph of the function, and it's defined at any point xy in this domain. So this should lie over this point here, and this, well, it didn't come out that accurate, but that's okay. Let's fix it just slightly to make it slightly more convenient, more convincing. Okay, clear? So what we're interested in now, okay, and again, this is just the motivating ideas behind the definition of the integral. We'll see that integrals have, as was the case in Calc 1, you can do many things with integral, not only measure areas under graphs. I hope you've seen that you can measure, for example, the length of a graph of a function using an integral in Calc 1. And you can even calculate limits using Riemann sums, and there are many things that you can do. But the motivating example is, we want to know the area. This is not good. This, oh, sorry, made a mess. This should be over this, like this. Okay, better. So what we want to know now is, it's not going to be the area. What's the word going to be? It's three-dimensional now. Right, the volume. We want to know the volume under the graph of f above the xy plane. We want to know the volume of this. Well, it's not exactly a rectangular box. Almost. The sides are all rectangles. The bottom is a rectangle, but the top is the graph of f. Okay, so we want to know the volume of this interior under the graph of f. Is that clear? Okay, and the way we're going to do it is by just mimicking the ideas from the single variable case. We're going to do a partition of this AB segment and a partition of the CD segment, and we're going to get some grid lying down here on the domain D. So if we partition like this and maybe like this, and I don't want to draw all the lines because then it gets blurry, but what you should see is that we're getting something that looks like this, some grid here in the partition, which breaks it into smaller rectangles. Do you see that? And each of these we're going to call, these are going to be the xi's, x1, x2, and here are going to be the yi's, y1, y2, etc. And each of these little guys down here, each of these smaller rectangles, and these are honest rectangles down in the domain, each of these is going to be of the form, its area is going to be of the form delta xi times delta yj. That's the area of a little rectangle down here. Do you agree? Where delta xi is, for example, delta x6 is x6 minus x5. And delta y17 is y17 minus y16. Clear? And now above each of these, we're going to construct, just like in the single variable case, tall and narrow box. You can think of buildings in Manhattan or in Hong Kong, wherever. A tall and narrow box, which is going to look something like this. Let me emphasize the word something like this, because these are not trivial to draw. So we're going to get some tall and narrow box here, and the top of that box, all of these are very straight lines, but the top is still the graph of f, right? So the top may look something like this maybe. Do you agree? Now, we choose a point down here. Let's choose a point and make it big and fat so we can see it. Choose a point down here. This chosen point, let's call it, SITJ. So we choose a point in each and every one of these little rectangles we get down in the bottom. And then let's evaluate the value of the function at this point. There it is. That's the value of f at this chosen point. And now replace the top of the building, the top of this skyscraper, which was originally the graph of a function. We replace it by just, okay? We just take a flat horizontal plane that goes exactly through this point. So it's going to look something like this. Okay, maybe I'll make a zoom view of this thing here so you can see it. So here's the bottom. This is this little rectangle living down in the xy plane. Here are the sides of the building. I'm going to make it shorter so I don't have to work all the way up at the top. This is dotted because it's in the background. Okay. The original graph of f was maybe something like this. Maybe this is the original graph of f. Good. We choose a point down here at the bottom, some point here in the domain. So this is the point SITJ. SI because I runs over all these different subintervals in the partition of the x segment AB, and TJs because J runs over all the different subintervals in the partition of the CD interval on the y-axis. We take the value of f at that point, which was maybe something, let's say, here. This drawing is not too accurate. Something maybe here. Maybe that's not convincing. Something here. And then we replace the top, which was originally the graph of f, by just a plane which goes precisely through this value. Okay, so we replace the yellow, the red top. Why did I say yellow? We replace the red top by the blue part. Okay, and now we get an honest rectangular box. Okay? What's the volume? Is everybody with me? Is it clear what's going on? The idea. Okay. What's the volume of this box? Do you agree that the volume of this box, just this single box, there are going to be many, many, many of them. So imagine skyscrapers with lots and lots and lots of windows, right? But you know what you see out your window? Right into the windows of the building next door, which is right next to you, right? Because there's another building here, and another one here, and another one here, and another one here. No space between the buildings. That's where New York is headed. Anyway, what's the volume of this thing? It's the area of the base. The area of the base is delta xi times delta yj. That's the area of this little rectangle down here. Do you agree? Times the height. The height is precisely the value of f at SITJ. Do you agree? Everybody? So this is the volume of one of these buildings constructed on the partition. But now we take all of them. How do we take all of them? We sum. And how many sigmas are going to be in this? Where did it go? How many sigmas are going to be in this sum? 2. One for the i's and one for the j's. Okay, so it's going to be a double sigma, which you could write like this, or you can write one sigma and put both indices under it. Both notations are fine. Okay, so this is the volume of one. This is volume of a single, let's call it box, rectangular box or building or whatever. And the entire thing, this is a Riemann, this is called a Riemann sum, just as before, and this thing is an S, a Riemann sum, which is an approximation for the volume under the graph of f above this rectangular domain D. Do you agree? Okay, so this Riemann sum, let's move to a new board. Before I write it, is the idea here clear? Does everybody understand what's going on? And so there's going to be the partition, and then in the box next door, there's going to be another building here looking something like this. And here is what the building looks like once we take the approximation, and before the approximation, the roof is the graph of f. Okay, and there are many, many of these buildings. I don't want to draw anymore because already it's starting to look blurry, somewhat blurry. But do you agree that because of the differences in the blue flat roof compared to the red avant-garde architectural roof, what we get is an approximation of the volume under the graph rather than the actual thing. And the way to make it a better approximation is to make these buildings narrower and okay. So how do we do that? We just refine our partition down at the domain. Okay, so we, instead of taking the interval AB and partitioning it into 6 subintervals, we're going to partition it into 600 subintervals, and there are going to be many, many, many more lines here and more lines here, and the grid is going to be very, 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 very delicate, and on each one we're going to get an approximation, but the differences are going to become very, very small, and in the limit, as the partition becomes more and more refined, in the limit, we're going to get the actual volume under the graph, which is going to be the double integral. Okay, so let's write all that. The Riemann sum, the Riemann sums, sigma I, sigma j, f of si tj times delta xi, delta x, delta yj. The Riemann sums of this form give approximations of the volume under the graph of f of xy above the domain D, which is a rectangle. In the limit, and again, this is not a precise statement. This is rather intuitive, but it's not the formal definition. You can imagine that the formal definition is going to have quantifiers, and it's going to have epsilon and delta hiding in there. For every epsilon, there exists a delta, such that if we refine enough the partition up to some delta somehow governs the refinement of the partition, then we can get that the difference between the actual volume and the approximation is less than epsilon. That's the idea. I'm not even going to write it. Okay, it's a rather subtle definition. Okay, I don't know if you saw the formal definition in Calc 1, which is not always given, but the formal definition of an integral, even for a single snake, is subtle. Okay, so in the limit, we get the volume, limit meaning refining the partitions, we get the volume denoted, the actual volume, denoted by, so we replace the double summation by a double snake, and the domain is going to be this D down here, and we write it underneath both snakes, and the function is f of xy, and we replace the deltas with dx dy. That's how we denote the volume under the graph, and this is just the intuition, okay? It can be defined for f not necessarily continuous, not necessarily positive. When the graph of f is negative, the contribution to this sum, the contribution of a part where f is negative is going to be negative, right? So we're going to be taking the volume above the graph of f under the domain D, just like in Calc 1, right? Okay. So is the idea clear? Is it clear what we mean by double integrals? Okay. Is the relation to volumes clear? Okay. So I want to formalize just a bit more, not a lot, and say the following things. So, yes. So one thing I did do was, if you can look here a second, I started with the rectangular domain. Okay, and there's no reason for domains of functions to be rectangles, right? And what we do, the reason I didn't start with just a bluish puddle down here of any shape and form is that then when we would have made this grid here, imagine a shape which is not necessarily a rectangle. We make a grid over it. The grid is not going to cover precisely the shape, right? There are going to be areas which are in the grid but are not in D, in the domain, and let's make a little drawing here. So let's write it as a remark. If D is not a rectangle, so think of some shape down in the domain which looks like this, which is a perfectly legitimate domain for a function in two variables. If you would try to do this process, you would make a grid here, right? Some grid like this, but there would be, let's say this little rectangle here. Part of it is indeed contained in D, and part of it is not. Are you going to count the volume of this building up here or not? And if you take this grid, for example, you're going to have here, you're going to have a rectangle which is entirely outside of this D. Do you see it? F is not even defined here. What do you do? So do you see that this poses a slight problem? Okay, you can't just divide it into rectangles because some of the rectangles are not going to be inside of D. Do you agree? Do you see that this is a bird's eye view of the domain? Is everybody with me? Okay, so what we do, so if D is not a rectangle, we give a further definition which is based on that definition in the following way. And this is a kind of a standard way to overcome issues of this form. So if D is not a rectangle, we define the double integral as follows. So assume D in R2 it still has to be bounded. It has to be a bounded domain. There is a notion of improper integrals, just like for single variable functions, but we're not dealing with those yet. So D is a bounded domain. And I'll remark, I won't even write it, it has to satisfy certain much more subtle conditions that allow everything to work. Okay, so some domains can be constructed which are just, let's say, a collection of points which won't allow us to do this thing. So any partition we take is going to have points outside the domain and points inside the domain, and we can run into issues here. Okay, so we still want D to be a good domain, and formalizing this good notion is something I'm not going to do. Okay, so if you think of some, let's say, connected, remember the notion of a connected set? Remember that? We discussed it when we discussed the intermediate value theorem. Everybody remember? Where any 2 points can be connected with a curve. So if you take a connected set and make it, let's say, closed and bounded and everything, and such that the boundary is a single curve, it should be okay. Okay, it's not trivial to think of those domains which cause problems. So let's ignore them. So assume D is bounded, and assume and let fxy be bounded, a bounded function. Again, we're not dealing with improper integrals yet, on D, defined on D. Okay? Let A be a rectangle containing D. So here is D. Let me erase this and draw it again. Here is D, bird's eye view of the domain down here. Here is D. I take some rectangle, whichever rectangle I want, that contains D. Here it is, some rectangle which contains D. Let's call the rectangle A. And I'm going to define a new function. Okay? Let D be a rectangle containing D. Sorry, let A be a rectangle containing D, and define a new function. We're going to call it f tilde of xy. F tilde is going to be defined on the bigger rectangle, on A. How is it going to be defined? It's going to be f itself whenever xy is a point in A. So is a point in D. So it coincides with f on this domain D. It's exactly f on this domain D. And it's going to be 0 when xy is not in D. So what you should imagine in this picture, where is the graph of f? It's out here, right? This is a bird's eye view of the domain. The graph of f is here. Do you agree? Everybody with me? So over D, f tilde is going to be the same as f. And on A, points of A which are not in D, so maybe I should write xy is a point in A minus D. Do you know this notation for subtraction of sets? So these are all the points in A, but not in D. Okay, on the complement of D inside A. So for points out here, we're just going to define the new function f tilde to be 0. Okay, so if we return again from the bird's eye view to the three-dimensional perspective, the graph of f is here. This is the rectangle A. Okay, the domain is somewhere here. It's f itself above D, and it's 0 outside. Okay, can you imagine that? Okay, and now I'm going to define the integral. out of space. So this is the definition. What do I want to do? I want to define the integral of f on this domain D. Okay, so we define the integral of f itself on the domain D to be the integral of f tilde on the big rectangle A. F tilde is defined on the rectangle, so its integral is defined via the process of making a grid here and doing Riemann sums and refining the partitions and so on and so forth. But the volumes, the little rectangles in the grid which are going to show up outside the domain D are going to contribute 0 to the Riemann sum. Do you agree? Because the function is just 0 in this area. Okay? So once we do the process, the integral of f tilde over the rectangle A is going to be the volume of under the graph. The volume under that graph is just going to be the volume of f itself above D. Does everybody see it? Can you imagine it? Okay, the contribution of what we added is not going to add anything to the volume. Okay, and this is well defined. This was defined previously. Okay, so in each of the iterations of the Riemann sums, there are still going to be here some little rectangles which have parts of D and parts outside of D. But as we refine, they're going to get smaller and smaller and smaller, and their contribution is going to become negligible. And in the limit, again, as we refine further and further, what we're going to get is just the volume under the graph. The graph is 0 outside, so it's just going to be the volume of f itself. Questions? Everybody good? Okay. So one more remark about this. There was something, I said, let A be a rectangle. And if you do this formally, you have to also justify that it doesn't matter what rectangle A you choose as long as it contains D. That it's independent of the choice of A. If you choose a huge A or a small a, you're going to get the same answer here, and therefore this is well defined. Okay, but we're not going into the details, so in particular we're not going into that detail. Okay? Okay, so now we know what a double integral is. Intuitively, it's the volume under the graph of a two-variable function above its domain. Okay? And what we're going to do next is two things. First of all, we're going to list a long list of theorems that kind of summarize the properties of double integrals, and they're going to be one-to-one analogous to the theorems for single variable integrals. Okay, so for example, the double integral of f plus g equals the double integral of f plus the double integral of g, and you should believe that that's true because of the volume intuition. You take f and g, pile them up, the volume under the sum is the volume under one plus the volume under the other. Can you imagine that? Okay, so there are going to be a bunch of theorems, and as in single variable integrals, all those theorems are not going to help us calculate. In order to calculate these things, well, the first thing we know is that we don't want to do Riemann sums. That probably is not the right way to actually calculate volumes under graphs. There's going to have to be some more efficient tool in order to do calculations. In Calc 1, that tool was the Newton-Leibniz formula, right? The integral from a to b of f is the antiderivative of f evaluated at b minus the antiderivative evaluated at a. That's how we calculated integrals, right? There's going to have to be some tool here. And let's leave that as a mystery, and we'll resolve it in the following clips.